Okay, so we're going to cover hierarchical latent models or bifactor models. So this is the example video from the lecture. It's going to go over both types of models. So the first thing we're going to do is just try a first order model. So just the measurement model or the CFA, because if the first order model doesn't work, then a second order model is not appropriate. So we should also be able to look at our correlations and covariances. And if they're not related, then how is the second order going to pick them? Or predict them, rather. So this step is important in the sense of making sure that the model is going to run, but it's also important to see if a second order model is appropriate. So if your correlations between latents is really small, it's going to be hard to say that should be predictive. So the first thing we're going to do is program this whisk model where it's got 4 factors, and this is the finalized model. So it's going to include 4 items for this one and then 2 for each of these other ones, which is actually going to cause us some trouble later. And so we'll talk about how do you deal with latent variables that don't have enough indicators really to make this sort of thing run very smoothly. So the first thing you want to do is import the data. So I have this file on Blackboard where you can open the R code, and it's already got all this typed out for you. But just kind of a reminder of what we're doing. If you're going to use those covariance or correlation tables, lots of data, meaning lots of columns, is easier to see if you stack it. So this is a covariance table, and I can tell it's a covariance table because the ones are not, the diagonals are not ones, and these are bigger than 1. But stacking it really made it easy for me to see that I hadn't missed a number, or and then I can kind of line it up with a table. So it's a good way to tell that I'm doing this correctly. So let's go look at that in R. So first thing I'm going to do is load both my libraries, and then I'm going to load that covariance table with the lower 2 full function. Alright. I have the standard deviations from whatever chapter this is from, 9. We don't really need them because we already have those covariances. And remember, you're converting correlation tables to covariance tables with standard deviations, but it doesn't hurt to have them. And so we can use the names function, that's for the standard deviation row names and column names to name everything. So I'm going to import those standard deviations and then name everything all at once. So if I look at my covariance table, I now have names for everything, and you'll see my standard deviation is a named number, so it also has names. So for the next thing I want to do is define that model, so draw the pictures. And so remember from the last chapter, we built our latents with saying latent equals tilde, so create this variable from these manifest variables, but it's predicting to the manifest variables because this is a reflexive indicator, so it's pointing outward. Okay. Remember, each latent needs to be on a separate line. So if I go back here and I look at this first latent needs to be created with these first 4 variables, so I would say latent equals tilde and then these 4. And that's how it's done. So GC is created from comprehension, information, similarities, and vocabulary. GF from matrix reasoning, picture concepts. Digit span and letter number for short-term memory. GS is coding and symbol search. So I'm going to run that. But remember, when you run this part and you're building the model, it doesn't actually do anything. That's just creating the template that it's going to use as part of the next piece of code. So let me back up. So we have defined our model, now we have to run it. So we're going to use that CFA function. So within the CFA function, it's model name, sample cov for our covariance table or correlation table, and sample knobs for the number of people, since we don't have the real data. So let's run that. So I'm going to save this .fit. And that ran pretty easily since it didn't give me any errors or warnings. The next thing we're going to look at is getting the output. So this is just really a summary. So as we go throughout the semester, I'm slowly going to use less and less slides to talk about the code, because at that point you should have an idea of how summary works. It doesn't really change throughout the semester. Anyways, we're going to turn on fit measures, R-squareds, and standardized output. And then let's look at that. So the first thing I always want to check for is Haywood cases. And I'm skipping ahead just a little bit to this interpret the output slide. So I want to make sure my variances and R-squareds look okay. Because if I have a Haywood case, this model is not acceptable, and so the solution is not worth looking at. So I skip down to the variances here, and they should all be positive, because variance is squared, and it is. Down here under R square, I want to make sure all of this is less than 1, and they are. And then in the standardized solution, something else you can look for is a correlation over 1, because you're not supposed to have those. So here under covariances, in the standardized columns, I've got some very highly correlated items, but none of them are over 1. Okay. Now, back up here. Some other things we can run, we can look at those parameter estimates individually and get their confidence intervals. We can look at our fitted covariance table and our residual table to see where we're estimating things poorly. We can look at those fit measures separately and look at modification indices. So let's do those one at a time here. So with our parameter estimates, remember in the standardized solution, what I want to see is that all of them load highly on their own factors. And so that is here. So getting used to looking at this type of output is really helpful, because when we get to modification indices and multi-group models, you'll have to use this type of output a little more. Okay. So unfortunately, because this code here, let me make it a little bigger, try running that again so they're all next to each other. There we go. So let's see, each item, and looking at standardize all, they're all very highly related to their own item. So that ends here. Right? So I got 0.86 and up, I'm doing pretty good. All the confidence intervals look good, and all the p-values are significant for the ones that estimated. The other things you get here, so these double arrows are variances, right? And these are the variances for the latent variables, and then the covariances down here. So these are correlations over here in the standardized column. What's next here? We'll look at the fitted table. So this is the table that it estimated given the model that you gave it. Let's look at our residuals. It's a little easier. And we don't seem to have anything too large. When we in a couple of chapters, we'll get to how to look at the standardized residuals. And those standardized residuals are, at least in z-score format, it's a little easier to read. But it doesn't hurt to look at them now. So the largest one is probably comprehension, matrix reasoning, but those are on different factors. So it doesn't make any sense to add any type of covariance between them. Coding and similarity. So a lot of these, the higher residuals are on things that are on separate factors. And so that's a little harder to predict because they're not necessarily related to the same thing. Okay? They're correlated with each other, but they're not creating that same factor. For our fit statistics, honestly, I find summary just a little bit easier to read unless I'm looking for a specific one. So let's see here. It is the chi-square significant, but whatever. We have a lot of degrees of freedom because we've moved into models that have lots of manifest variables and not as many parameters. Our CFI and TLI are really good. RMC is also really good, so is the confidence interval. And SRMR is also good. So this is a well-fitting model because it's made-up data. And then the last thing we want to look at maybe is modification indices. Even though the model, I would probably say don't do anything because the model already fits really well. But let's go ahead and look at some of those modification indices. And there is a way to sort them. So let's see. This is in code later in the semester, but let's see if we can figure it out now. Because it would make life a lot easier if we could sort these bad boys. Right? So let's see. Power sort dot equals false. I knew it was something weird. So let's add here sort dot equals true. And that gave them to me at least in order. Woohoo! So that makes it a little easier to read for you. So the worst fit, unsurprisingly, because we looked at this in the residual table, is between comprehension and vocabulary, comprehension matrix reasoning. So here, remember that the MI, the modification indice, is a chi-square change expected if you add this path. So this would be how much chi-square would decrease if we added that particular path to our model. Now, when you're doing these sorts of things, it doesn't help to add things on, add correlated error terms, because that's what this is. It's a correlation between these two, which makes it a correlation between the errors, if they're on separate factors. So if I go back and I look at what this model looks like, comprehension and vocabulary are actually on the same factor. So I could probably correlate their errors and get away with it. I'm not going to, because this model doesn't really need to, but that sort of thing is a case where I could. These two are on different ones, so I wouldn't want to do that. Technically, anything over 3.84, which is the cutoff for chi-square for 1 degree of freedom, is significant change. But looking at these, a lot of them are probably not an appropriate change, right? And you don't really want to screw with a model that's good anyway. This one would be a double loading, so I don't know if we want to do that. But looking at them doesn't ever hurt you. Let's create that picture. So it's model fit, what labels? I have standardized labels and a tree layout. And that gave me the picture that I had in the notes. So I can see that those correlations between items are very high, between latents, and all the loadings are really good. So anytime you have that kind of super high correlation, brain fart. Anytime you have that super high correlation between latents, a second order model would run well if it's theoretically appropriate. And that's the big question. So in our first order model, it looks good, ran nicely. We find that those correlations are real high. So that's a good sign that maybe a second order model would be appropriate if theoretically understandable, or potentially we should collapse factors so they're not distinct. But the purpose of this chapter is hierarchical models, so we're going to build a second order whisk with G as our second order predictor. And so this is the sort of ubiquitous IQ-G component. But when we do that, now we're going to have error terms on these latents instead of variances, but they're going to be unrelated to each other. So we're actually dropping a lot of estimations of covariance and adding in just a couple of estimations of direct paths instead. Now, we're going to try a second order model, and there's going to be some interesting things we have to do to make this work. So there's two different ways to identify that section, because you have to identify both the measurement model and the second order piece. The first thing you can do is set the variance of the latent to 1, but not set the lower level variances to 1. So I can leave these as marker variables and set the variance of this latent to 1 without automatically setting these, because otherwise with a standardizing on the latent variable, it will set everything. Focus everything on the latents. So what we do is we say G equals, and then we add our 4 latents together. But you do the first one here as NA times. And that is a special piece of code that stops it from becoming a marker variable. And so that turns that off. And then what happens here is I get double tildes equals the variance. So I'm setting the variance of G to 1. So this turns off marker variable. This turns on setting it to 1 without adding standardized equals true in the CFA component. We've been leaving that off because I've told you that you could look at both if you leave it off. The other thing you could do is set a marker variable and set one of these paths to 1. But I think this is more common in a sense because I want to understand how these are all loaded instead of setting one of those. Now, what I've done in this particular picture is this one does have a marker variable. So that's why I got the dashed line here. And then I looked at the standardized output, which does basically the same thing. So let's try that. So the first code I have here is setting that variance to 1. And then I included the code of what you would do if you didn't want to do that, if you wanted to do the marker variable. So I'm going to run this with the variance set to 1. This piece, the CFA is the same. So you see we don't have standardized in the CFA because I don't want to lose information. And let's look at the summary. Okay. First thing I'm going to do, make sure your variances are positive, your R-squareds are less than 1, and none of this should have changed. So what's happening here is all of these should stay roughly the same, or basically the same. And what happened is instead of having covariances, so if you look at the last output, we have covariances, now we have direct paths. So we dropped those covariances and added direct paths between them. And so all of our standardized things out here, components should be roughly equal. Regression coefficients. These are very, very strong. So this model worked well. If I go up and look at the fit indices, they will not have changed. So this is an interesting component, or they will have changed like very slightly, because we have changed some of the degrees of freedom. But it all ends up working out the same. Hold on, let me show you this one. So we've moved things around, but we've kept the same fit. So you can't actually compare these models to each other because they're the exact same degrees of freedom. What you want to see is that they come out pretty much the same. So look at this CFI, 991, 986. If I come back down and look at our higher order model, my CFI 989, 984. So it's approximately the same. My chi-square didn't change at all, actually. So let's see. That's because I'm looking, this is the baseline model. Derp derp. Sorry. Here's the real model, not the null model. So I've got 5818. Let me go back, scroll up real quick. Sorry, clicking the wrong buttons. Okay. And I have 5818. Okay. So that stayed the same. Higher order fit. Let me make sure I'm looking at the right one. Oh, and then I looked at the wrong one. Oh my gosh, you guys, stop me while I'm ahead. Here we go. Here's the other one. So it changed just slightly, but see what's really happening is the degrees of freedom are moving around. So we have less estimated things. And so this model is actually simpler because it's got less parameters being estimated because we've dropped some of those covariances and just made them direct paths. All right, third time's a charm. So let's see here. With this one, let's see if it fixed any of our residual problems. So we do still have some pretty big residuals between some of these variables. And so that will come up if I look at modification indices. I should still see the same problems. So we've got sort dot equals true. Right, so I got more of them. Let's see. Same ones at the top. So the problems don't really go away with this particular type of estimation. You're just saying, look, these fit the same. So a simpler model, a structured model, is probably more likely. So let's make that pretty picture. So this one will be slightly different from the one I have in the lecture notes because it's got the dots out here because I ran that first one where I standardized on the latent by setting it to 1. In lecture notes I ran the second one where I did the marker variable and they're roughly the same. So we've looked at all of the different pieces for the second order model. So no Haywood cases, R-squared looks good. Our parameters should stay roughly the same. If you've got very large changes in parameters, that is called interpretational confounding. We'll talk about that more later. But essentially the problem is that this model's not invariant, which is bad. You want the model to stay roughly the same because you're really actually just making it simpler by adding in this predictive points instead of having all the covariances between items. We still have the same issues with residuals, so we got the same modification indices, and our fit indices looked really good. So that is how you do a structured second order model. Let's talk instead about bifactor models. So bifactor models, let me delete this so you can read this, are very interesting because they are so conceptually kind of different. So instead of having G be structured as a higher order component, right, so G leads to these things, which leads to the output you see. Instead, we say, well, all the variance should come over here to G first, and then we've got these other secondary domain-specific areas, and those hopefully are still significant after controlling for G. But the setup on these is a little odd, so you'll see you have all these different little arrows here that look like they're covariances. If you remember from the lecture, I said you don't covary them, but if you zoom in real close when you make your picture, you'll see that those are set to 0. Okay. So let's define that model. So I'm down here where it says bifactor model on line like 92. And we have to set this one up in kind of an interesting way because of the number of indicators per item. So let me go back and look at this picture real quick. And we've talked a couple of times about identification and the number of paths that you have. And so with items with 2 indicators, you really have to have, brain fart, you have to do something. Because normally you would just set a marker variable, but that doesn't really work in this type of model because I have extra, I'm using up extra degrees of freedom to predict each variable twice. So each manifest variable is going to have 2 arrows going into it. And so that really causes a strain, so to speak, on these particular variables with only 2 items. So I have to add in some extra constraints to control for the fact that I've included all these extra degrees of freedom. Now, the degrees of freedom will be fine in this particular type of model. The issue really becomes the each little separate latent has to be identified. And so with only 2 items on this particular latent, or all 3 of these, that's where it becomes a problem. So this particular code, and this is special to when you have 2 indicators per item and we're running bifactor models, because if you look at the original model that we ran, even in the higher order I don't have those little letters. So this is a specific problem to this example. But it's a good example to show you of what happens when these things, when you have this particular problem. So what's going to happen is we're going to set both of these to A. So we're requiring GF to be made from matrix reasoning and picture concepts, or it predicts matrix reasoning and picture concepts, but we're requiring that each of those paths be the same. Now I've just called them both A here because I'm trying to match the book. You could call them both Swiss G's, as long as the name is the same across them. So anytime you have those little multiplication things, it will use those to label them, and if they have the same label, it will estimate them as the same number. So you'll get the average of both of them. That's what will happen. And so we have to set them to equal to get identified. So I'm actually going to turn that off real quick, just so you can see what happens when your model isn't identified. Which you've probably had that happen if you've played around with a lot of those path models. That sometimes will lead you into problems with identification. Okay. So let's say we had just copied the model from above and we changed G to just predict every variable instead of our latents. Okay. So nothing's going to happen here because I'm still building the model. Now let me try to run that model with my CFA. Okay. And it gave me a warning. It says, can't compute standard errors, don't know what the hell is happening, the model is not identified. Okay. And so that really is why I have to include these constraints. So let's try running it for real now. Now, let me talk about this other little thing. So after you define those latents, so your normal CFA, you're going to add a second latent variable that everything is related to. So this is the bifactor part. Each item, each manifest variable has two factors. The generalized factor and then the domain specific ones. So I just added everything together. And then in the CFA line, the part where you actually run the model, you have to add some code so you make sure you get your covariances between latents as turned off. So you could manually set each one as like G tilde tilde 0 times G, but that might take forever if you have a ton of latent variables. So this nice little piece of code, orthogonal equals true, turns off the latent correlations. So it forces those latents to be uncorrelated, which is much faster than doing them one at a time. So you'll see I have this little piece here, which I didn't have above. So with a hierarchical model, you don't want this, but with a bifactor model, you do. So just a quick note, I am not looking at the standardized solution, the book does. And especially because if you run this as a standardized solution, only the model pictures won't run for some reason. Alright, so I ran that. I got no warnings or errors down here. So let's look at our summary. Come back over here. And so let's see what happens when we look at first Haywood cases. So all of our variances should be positive. All of our R squared should be less than 1. Great. I have no correlations to look at, so see, they're all set to 0. Now let's look at the standardized solution here, which is really more appropriate because look, see, all these are 1s, and that's not very helpful. So if I look at the completely standardized solution, I'm really actually interested in G first. So I want to know that they load on their generalized domain first. So if none of them load on that, that implies they're not related to the main factor piece I'm interested in. So it's like I want them to be loaded on the generalized, and then that's a control, and then what's left over really is the question with the bifactor. And so for each of these, they load very nicely. They're all very strong. It's significant. Now after accounting for that, do they load on their domain specific areas, or is the whole thing accounted for by the generalized one? So looking at GC here, those 4 all load up. They load fine. They're over 0.3 and they're significant. Okay. I won't get any significant values here because I didn't turn on the standardized solution. If you turn on the standardized solution, you will get them. But this is kind of bad. So these are kind of low. Right? So we should check and see if that's significant. These are also kind of low. So you might argue that these two don't exist after you account for your generalized G. And then this one looks fine. Okay. So these two here are questionable because do they still exist after a control for G? So if I wanted to see the z-scores, okay. Unused argument, oh, sorry, wrong place. I would need to not do it there. I would need to do it here as part of the CFA. So let's run that real quick. Now I'm going to get p-values for all of them. Okay. And so even though these are small here, they are significant. So it's up to you whether you want to argue if they still exist or not. I would say those loadings are pretty low. These are kind of close to our generalized 3 variable, but they're certainly not nearly as strong as our GC and GS. So you can kind of rank them if you think like this is clearly still a pretty moderate factor. This one's still a pretty moderate factor, and these two I would say are a little weaker. And you'll see that as well in the R-squared values. So for each item, we can tell picture concepts is not going so well. So it has a fairly, oh that's variance, sorry, wrong one. Picture concepts here, it has pretty strong loadings, but because the loading here is a bit weaker, it's not accounting for as well as some of these other variables. So those might have some bigger errors in them. Now I'm going to go back and take this off real quick. Alright, so let's look at our residuals here. Oop, wrong way. So our residuals are kind of much smaller than they were before because I have them being accounted for by two different latents. So that's naturally going to lower the residuals because I have different places for the error to go. We didn't look at fit statistics. Let's look at that. I keep hitting the wrong one. Let's see. So CFI very strong. TLI also very strong. Look at this output. So here's RIMC, it's good. Upper and lower are well below our good cutoff. SRMR is very good. So I would say this model is really good. And then let's look at modification indices. Can't hurt. And we were adding sort equals true. I get tons of them here. And so I still have the same ones at the top, but if you remember from before, that modification indice was much larger. So now my error has gone down some, and so I've accounted for variances a little better than maybe the other model, but they're both like very good fitting models, so I think it would be hard to argue that one is better than the other. And that might be a theory thing that you would have to argue over, because I bet they're very similar. Okay. Oh, right. So if you run this as standardized equals true, this bad boy doesn't run. I don't even think... Yep. It doesn't like something about the way that runs. It doesn't like it. So I want to rerun this without that standardized. Oh, that's just a summary. Wrong thing. Now let me go back and make this picture. I know the picture works. I did it a minute ago. There we go. So all of these are 0, and they're dotted because they didn't really get estimated. Now these are kind of dotted because they were constrained to be the same thing. And then here's the marker variable for G. So it looks like you forgot to fix your covariances, but it's really tiny, but they are set to 0. So that together is hierarchical and bifactor models. They don't always both fit very well. Sometimes one will fit better than the other, and so you can argue for, hey, this one fits better, so it's the more appropriate model. If they both fit about the same, then it comes down to a theory argument of which one is a better interpretation of what you might expect given previous research.